Okay, today I'm gonna show you how catchment delineation is done in QGIS using WhiteboxTools. I've already downloaded DEM from my subject area, that is Warwick Farm near Liverpool, Sydney, Australia. I'm going to delineate catchment for Brickmakers Creek today. So the first step is to fill depression, and the input file is downloaded DEM, and the output file will be fill DEM. This process will fill all the depressions so that the flow of water is ensured properly during the catchment delineation process. Okay, it will take time depending upon the size of DEM. The file is already there but not displayed in the QGIS window, so it will take time. Yeah, there you go. There's the file. I close the dialog box. Yeah, I can visualize this one. Okay, there. The next step is to find flow direction, and in WhiteboxTools it is done by D8 pointer. I'll input DEM field as an input raster, and the output will be flow direction D8 pointer. This is nothing but the flow direction of each and every cell. There you go, that's flow direction raster. I can close the dialog box. The next step is to find flow accumulation raster. I will simply use fill DEM as input, keep everything as it is, and the output I'll name as flow back. Every cell contributes to another cell which receives water, and that's stored on the raster cell. The drainage point, let's say the outlet point of the catchment, will have the maximum accumulation, so that let me check the value of flow accumulation of the drainage point. I'm searching for query tool, information tool. Okay, it's on the view and identify features there. I click that raster, it's a huge number over there. That means it receives water from those numbers of cells. To delineate the streams, we generally use 10% of this value. I'll show you how the next step. Okay, the next step is extracting streams, which we'll do by extract streams. There we'll use flow accumulation there, that's correct one. And generalization threshold, I will use 0 now. We'll use different value later to show what's the difference. So I'll save it under name extract stream. There, you can save and run. Close. There will be many streams on doing so because every cell will be the stream, as I provided 0 for channelization threshold. Let me provide 10,000 and save extract stream 1 as another file. I think this is wrongly made, which I can remove the first file and newly created this one as well, because nothing is there and I can't see it properly. Okay, there's huge number over there, so I can get rid of that one as well. Okay, I'll do next trial. Use flow accumulation there is 2000 as generalization threshold. We can find this number by hit and trial, and this is my third trial. Generally it is 10%, sorry about that, 10% of flow accumulation value of drainage point, but now I'm using 2000. That means I will have a lot of observations at the end of this process. Okay, I can turn off everything and see there the stream are delineated here. Okay, the next step is to convert these raster streams to vector 1. So the input will be streams, extract streams, pointer file, there you go, and the output file will be simply reverse and will be in save file format. I will create new folder to save files there and just save reverse there, save it. I'll check everything is fine or not. Yeah, there you go. Because I've got reverse over there, but I can see the projection system is not defined for the newly created reverse. So I will define projection system for that. It's Zone 56. Sydney is in Zone 56, so I need to get that projection system over here. I know the DEM is in Zone 56, so I can just go there and click that and click OK to display it in there. Okay, I can now select, and the reverse save file is now in projection system, the required one. Now for the drainage point, I will create new save file layer. I will name that as drainage point. Drainage point. Save that. The geometry type will be point, and the projection system GDN94 MGH156. Edit that. I know the point, so I will just define a point here and save it. The next process is to snap PowerPoint. We'll use Jensen snap PowerPoint. The drainage point will be taken as input, and the input stream file will be raster extract stream 2 there, and within 20 meters of the drainage point it will capture the streams, and I will save this file, this point, as drainage point final, just like that. And now I can simply run the process to get the new drainage point, which snaps the river stream. We can see the new point is exactly the stream. Now we'll simply delineate the catchment by using watershed D8 pointer file, the PowerPoint final, and the output file will be raster. I'll save under raster and that's the catchment we want. Okay, the catchment is delineated. Now we will convert this catchment to polygon catchment so that we can have different attributes of it. For example, catchment area, catchment, polygon boundary, etc. So the tool is raster to vector polygons. The input is catchment, that's fine. The output will be save file and it will be named as catchment so that it will be easy for me to understand. Okay, there you go. And done. Just the catchment. I can change the property. There. I'll make it transparent. And let's say I'll choose red and 0.46 as a stroke width. It will make it a little bit bolder than other. I can turn off all the layer and see the catchment there. And that's the reverse layer. I can just clip the reverse and give the reverse within the desired catchment. So I will clip vector by mask and I can save it on the reverse within the catchment like that. Simply save. Sorry, run and close. It will take time. There you go. I will define the projection system and I can simply turn off the reverse layer there and I can see the reverse within the catchment. So we can also determine longest flow path for this catchment. There's a tool. It makes really simple. Just provide the required DEM files and it will give us the longest flow path. This is very important in hydrological analysis. Yeah, there you go. Yes, there's longest flow path. I can change the property of it so that it will be clearly seen. I can go DEM, change it to blue color. Sorry, what I did. Okay, I can simply close the dialog box and repeat the process again. Okay, I'll close it. Repeat the process again. Yeah, I'll make it blue so that it is identified as a string there. I will change the stroke width to 36. Okay, there you go. That's the longest flow path for this catchment. Now I'll define subbasins. I've told you earlier that the subbasins will be really small because the channelization threshold was only 2000. Ideally, it should be 10% of flow accumulation value of the drainage point raster, so there will be really high number of basins in this process, which we can control on define streams step. So we'll simply see what will happen. It will take time because there will be a lot of subbasins. So here are the subbasin. I will convert these rasters to vector using raster to vector polygon tool under WhiteboxTools. Yeah, there, subcatchments, and I'll save this into catchments there. Subcatchments. It will take time. Definitely there will be huge number of subbasins and it will definitely take longer time than usual. Having subbasin will be really helpful during hydrological modeling. It will divide the catchment area into smaller catchments so that we can accurately define the subcatchments and their imperviousness values, the gradient, and every hydrological characteristics so that the result will be similar to the real one. So having subbasin or subcatchments is really beneficial in hydrological modeling. Yeah, there you go. There are so many subbasins. I can simply close that and I can only have subbasin within the catchment only, so I will use the clip feature again. Like that, input layer will be subcatchment and max layer will be catchment. I will simply save it as subcatchment within catchment and run the process ensuring everything is right. That's just a warning, you don't have to be worried about that. And now, yeah, subcatchments within catchments is there. I can simply uncheck subcatchments there and have subbasins because we have provided channelization threshold really high, so there are large number of subbasins.